moderating a very important webinar. Today, we are talking to two key companies in the silicon photonics value chain to understand the preferred future towards linear pluggable optics. And I had the honor to meet today with me Pierre, the co-founder and global sales manager of Luceda Photonics, and Joseph Ben-Ezra, the chief technology officer and co-founder of NewPhotonics. Over the next hour, you're going to hear about the most impressive things that these two companies are doing and how, and this is where I come in, how these two companies managed to find a way of working together. We go to the next slide, then we can see what's going to happen on the next hour. First, you're going to hear from Joseph Ben-Ezra about the LPO market overview. For those of you who are not really familiar with linear pluggable optics, we are really trying our best to decrease the power consumption and cost by removing the DSP of the pluggables. And New Photonics has a very interesting way of doing that. Afterwards, we will hear the counterpart on the chip manufacturing from the photonic design platform of Luceda Photonics and how the dreams of New Photonics can be matched to the reality of the foundries through the software of Luceda. And with no further ado, please go to the next slide. I would like to remind everyone, all of you to have joined this meeting, please post your questions in the chat. We want to hear from you. So all these people who have joined today from different companies, such as, for example, Alcyon Photonics, Nokia, please write your questions in the chat. I will make sure that they get answered in the room. With no further ado, let's start. I would like to give the floor to Optica corporate member, CTO, and co-founder of New Photonics, Joseph Ben-Ezra. Dr. Ben-Ezra, the floor and the attention of everyone goes to your linear pluggable optics. The floor is yours.
Okay, thank you, Jose, for introducing NewPhotonics and Luceda and opening the webinar. Yesterday was a Photonics Day, so we are continuing the celebration of Photonics. So this is the very beautiful example in the field of integrated photonics and collaboration between two companies, NewPhotonics. NewPhotonics actually was established 4 years ago. We are a fabless company. We are designing, developing, and we are manufacturers of photonic integrated circuits. Especially, we are focused on artificial intelligence era, data center applications, and what you can see on the bottom of the slide, that our solution was recognized as most innovative photonic component, and we have received the award during ECOC 2024. So we have now a chance to describe what is the product and what are the specific characterization of this one and what are the problems we are solving. So please go to the next slide. In order to put the things in the right contents, please pay your attention that a few years ago and right now, a single Google search can power a 100-watt light bulb for 11 seconds. But today we are using also ChatGPT for various purposes, and you can pay your attention that the same search using ChatGPT requires at least 15, 100 times more power than a single Google search. So the power is an issue. So we are actually resolving the issue of the power, reducing significantly the power consumption of the transceivers used for the interconnectivity between the CPUs, GPUs, GPU clusters, etc. We also reducing the complexity of the transceivers, latency, and definitely the cost. And I will try to explain how we are doing it. So next slide, please. The traditional solution for the transceivers is based on DSP, digital signal processor, which is a part of each transceiver. Actually, it's not a real digital signal processor. It's more dedicated signal processor because you cannot really, it's not a programmable device. It's some very limited functionalities. But it's very important component in the transceiver. If you are considering 1.6 terabit per second transceiver using 8 lines of 200 gigabit per second, the power consumption of this transceiver is about 30 watt. It's a huge problem because if you are considering the switch with the 25 50 terabit per second, you have hundreds of these devices. So the power consumption, the heat dissipation is a very huge issue. So the industry is looking for reducing of this power consumption, and there are some solutions, emerging technologies like LRO, linear receiver optics. In linear receiver optics, they are reducing the DSP functionalities, and DSP is just used for the transmitter, the transmission path. You can, in this way, reduce the power consumption from 30 to 15 watt. Another emerging trend is LPO, linear pluggable optics. In linear pluggable optics, we are eliminating DSP at all. Some functionalities for channel equalization are implemented in drivers and TIAs. In this way, you can actually achieve reliable communication, but you cannot achieve interoperability, especially when you are talking about 200 gigabit per second lanes. Due to the trace differences, due to the RF design, which is different from vendor to vendor, you have different channel impairments, and now without DSP, it's almost impossible to overcome these impairments, to mitigate these impairments. So what is our solution? Okay, so you want to reduce the power, you want to reduce the complexity, you want to reduce the latency. Okay, once you are removing DSP, you need something else. And something else you need, it's optical signal processor. We are implementing almost all functionalities of DSP in optical domain, utilizing passive optical components for those functionalities. In this way, we are reducing significantly the power consumption, the complexity, the cost of the entire solution. So, main takeaways: we are achieving the consistent performance, real interoperability between different vendors, reduce the system power consumption, and definitely we are reducing the cost, replacing the power-hungry and costly DSP on optical signal processor. Next slide, please. So, in order to understand how it works, I will a little bit introduce the techniques used for the channel equalization. The main purpose of channel equalization is the improvement of the channel performance, improving the bit error rate of channels, keeping some margins. The techniques used for the channel equalization are FFE, feed-forward equalizer. Feed-forward equalizer mainly implemented at the transceiver side. It's actually three-tap finite impulse response filter, which can equalize the channel by emphasizing high frequency part of the signal. Actually, you have a precursor, postcursor, and main cursor. And if you can adopt those cursors according to the channel impairments, you can improve significantly the inter-symbol interference, etc. Another way doing it, it's just a moment, please. Can you go back? Another way is a decision feedback equalizer. Decision feedback equalizer is implemented at the receiver side because it requires the feedback. Actually, based on the received symbols, you can adopt the filter coefficients in order to reduce the inter-symbol interference in the channel. And another way is continuous time linear equalizer, which is actually implemented as an analog device. It can be passive, it can be active, or it can be combination of passive and active using amplifier. You can see on the right side of the slide how we can improve the eye diagram and opening of the eye diagram using CTLE for different attenuations introduced in the channel. This is the example from the Keysight Advanced Design Studio. It's a very important tool when you are working with the different vendors and you have ABIS models of the CERDES and you want to implement your solution based on the electrical or a photonic solution in order to improve and overcome the impairments of the channel. So you can see how the eye diagram is opening when you choose the appropriate parameters of this CTLE, and you can see also the improved impulse response of the entire channel. Next slide, please. Before going to the ADS, there are some existing tools also in the MATLAB in order to understand how you can design your equalizers, both FFE, DFE, or CTLE. Here I'm showing the example when you have 0 dB loss channel, comparing with 8 dB loss channel PAM4 diagram. You can see that on the right side, the eye diagram is completely closed. Next slide, please. So when you are adding FFE and CTLE, you can see the improved eye diagram and improved impulse response of the system. So these are the theoretical principles of the equalization. So main idea of NewPhotonics actually to implement those functionalities using photonic components, because theoretically it's possible to implement finite impulse response filters in with photonic devices and photonic components. So our product is actually designed for transmission of 4 times 224 gigabit per second or 8 times 224 gigabit per second per lane channels. We have monolithically integrated laser array modulators and our optical signal processor. Optical signal processor is placed immediately after the modulators and responsible for the mitigations, overcoming of mitigation of the channel impairments, both in RF domain and also in optical domain. Next slide, please. So before we are going to the Luceda part, I want to emphasize few things. Designing the photonic integrated circuit, once you have an idea and you have enough knowledge, doing it's very important, but it's very small portion of entire game. Because in your game, you have to consider the wafer level testing, the manufacturability of your design, the packaging of your design, both RF, electrical, analog, digital, and optical packaging is a very, very important issue. So in the design process, it's very important when you're choosing the tools to choose the right partner, having also the understanding of the entire chain of photonic chip production. And we found that Luceda is the right partner working with them because they have very high professional team and tools, and they can support each stage of this development. Pierre, please continue from this point.
Sure. Can you hear me?
Yeah.
Loud and clear.
All right, awesome. Thank you, Yosef, for this endorsement. I can only say that it has been a pleasure working with you. So far to bring NewPhotonics to new heights together. My name is Pierre Wahl. For those that don't know me, I'm one of the co-founders of Luceda. And here I will introduce the Luceda Photonics design platform in the context of LPO. It is a platform that's, of course, a lot broader, but I will emphasize the aspects that really helped Yosef and his team to bring products so close to the market. So to introduce Luceda and the Luceda Photonics design platform, we are really a photonics design company. So our customers are designers, but we are also an ecosystem company. So we work with everyone in the value chain, from foundries to designers, other software suppliers, assembly partners, testing partners, trying to, in the digital domain, expose the entire value chain. And to Yosef, and we have products that are built with Python, that are a code-driven flow, that bring together all the aspects of design in the virtual domain so that people can make chips that fit into products that work. So our core products are Luceda IPKIS, which is our flagship products, and is the platform that centralizes all the design aspects, that contains component and circuit layout, optical and electrical routing, and all sets of solvers that ultimately leads to GDS export. And also we have links with partners, which I will talk about later as well. So one of the things Yosef said in his presentation, which is very important, and I took the liberty of borrowing his slide and adapting it to our colors, is to bring the constraints of PIC manufacturing and PIC assembly and test into the design process, so that a lot of the design iterations that would be required can be avoided, and working towards our goal of first time right on all design aspects and productifications of PIC-based products. So inside what is coming forward, I will try to emphasize how this plays out in several sub-circuits and sub-aspects of what the LPO component, what of the designs that are very close to what, but not identical, and I have to mention that explicitly. They are really not completely the same, but they are related. to what NewPhotonics is doing. So when you think about PIC design, typically PIC design is about optical design of optical components. And what do I mean by that is things that are not in the foundry PDK. Every designer out there still today uses components that are not of the PDK. So like a mature design tool needs to take into account constraints from the foundry and be able to present a flow to create components. And that's even true when you're operating at wavelengths that are telecom. The PDKs are still not complete today, and they need to be augmented. And that is a flow I will present here. Next is the optical subsystem design. So when you're putting components together and creating a circuit, also here you have elements of the design synthesis that need to take into account the entire manufacturing chain. And finally, before you tape out, you need to make sure that you take into account the constraints of assembly and test. And there it's not as, I will also point out the things Luceda is doing to facilitate that process. Ultimately, we want all our customers to ship products that make them money. That's the name of the game for the entire ecosystem, right? And I think everybody wants that. So let me dive into optical component design. So what we do here is to bring together all the constraints that come into component design. So what we do is we use a standard language, Python, and build up parametric components. So that's really standard. That's something that's been around for a long time. And we have a concept called virtual fabrication. And that is something that's very important. So inside the Luceda PDKs, all the materials as qualified by the foundries as much as they can, and their process in the virtual domains are represented. That allows that when people are layouting and setting out the shapes of their components, they can be built into the 3D structures that can be pushed to simulators. And the simulators are sometimes our own, but most of the time they're not. And as an ecosystem company, we build links to push these 3D structures that reflect the material properties of the devices into tools like Numerical, Tidy3D, CST, and others, or even the internal tools that are built up by our customers themselves when those tools are not good enough. That happens as well. So we centralize everything into one Python flow. And what we do then is we create what's called simulation recipes. And simulation recipes are something that centralizes all the IP on component creation. And imagine just an example. This is in this case with Numerical. You have a directional coupler that you want to be parametric. It's a very standard component. Sometimes it's part of PDKs, but sometimes it's not. And you want to be able to vary its length to change the coupling ratio. It's a very common case. What do we do is what everybody would do. You would sweep the directional coupler and get some simulations out and build a parametric model to be able to predict the coupling ratio of each one you put on the device, right? And so this is something that one can do through our framework. We fit the parameters, we build a design heuristic, and we have a parametric analytic model that will be able to predict the directional coupler behavior for a wide variety of parameters that you can set. So you can use it in the next level. And not only do we bring that together we bring that together also in the code aspect of things. So this is just for the people that are Python buffs out there, but just to project the organization that we bring to your design flow. Imagine a directional coupler into your library that you make yourself. It contains everything you need to know about it. The data that you have validated, the documentation, the P-cells that are reflecting the parametricity of your components, the simulation recipes that will take a layout, fabricate it according to foundry rules, and generate a model, as well as the scripts that will do all the fitting and the analysis of those simulation results. So imagine you have an engineer in your team, and that person is doing component design. All of his contributions, all of his IP are neatly organized in one place. That means if that engineer is promoted or moves somewhere else, you are still able to do his or her job. And that's something that happens a lot, we know, and it's part of your company IP, and you can consolidate it. So when we move to system design, I took two simple examples out, right? So This is like a passive filter that is similar, but not the same as to what NewPhotonics is doing to do the OSP. And when you do passive de-embedding, you basically apply a synthesis algorithm around a filter. So to be able to have a FIR filter in the electrical domain has a relationship to a FIR filter in the optical domain. There are lots of publications on that, and they are quite technical, but you can relate those two. And so that means that you have what we call a synthesis algorithm. A synthesis algorithm relates the behavior of the system to a design. And that is, in this case, not so straightforward. There is some mathematics that are involved and a lot of know-how on how to do that best. And here, what we want is one flow that is able to take into account the simulation, the synthesis, and the layout parametrically according to the constraints imposed onto you by the system, the foundry, and the components that you're using, right? And so that's exactly what we do at Luceda. So we have the ability inside our parametric framework to bring together the synthesis that we code, the parameters of your high-level system, and be able to generate transfer functions that fit the behavior you need. And that's really exactly what happens in the passive element of the OSP at NewPhotonics. They have very advanced synthesis algorithms that relate their high-level boundary conditions onto circuits that work based on components that work. And all of that can be adapted to different changes in the operating conditions of the chip that you want to make, the foundry that you want to use, and so on and so forth. So it's a very flexible design tool that allows companies like NewPhotonics to quickly target new applications. The same is done for active components. There we bring a certain, for active components, we see among designers that typically people combine PDK components and components that they design themselves. Typically, the actives are tailored to the applications, while the passives in modulator schemes are not, or they come from the PDK. And so we allow here again the same thing, a parametric framework where you can interchange like components that you do yourself and those that you want are coming from the PDK and assemble them into a circuit. Here you see like a coherent modulator that adopts this scheme of thought. And the behavior of this modulator will be simulated according to models that are done at the basic building block level. So if you have a very good model for your phase shifter, you will be able to extract a model for your entire modulation scheme, and you can send signals in, signal out. These signals can come from electrical simulators or even from like measurements that you, like signals that you prepare for doing certain quality sets, so like TDQ signals and so forth. So you can load in those signals, see what the output is, and simulate in the virtual domain the behavior that you want to have. And not only can you do that, you can also automate the analysis of those components. So particularly when you look at signals that are very complex and you need to do an analysis of the signal, look at I diagrams, look at bit error rates, look at TDQs, bit error rates, and things like that. You can put all of this analysis in code and then basically get out the figure of merits you want. So again, here is another example of what we do for a higher modulation format here. So again, what I want to emphasize here is you are able to stack up all the IP in terms of a system like optical subsystem design into one framework where different boxes can fit into each other and create a behavior, a layout, and a simulation, and an analysis that fits together. So once you're done with the sub-assembly or the design of the sub-modules. You need to put things together. And there you really need to leverage more of the value chain, right? You need to take into account who are your partners for assembly. And again, I want to emphasize this about us. Luceda is an ecosystem company, and we work with everyone that's willing to work with us. So we have a couple of assembly partners, Alter, Fix, and a couple of others in the pipeline that work with us to help them build their digital twins. But there I have to also make a confession. We are not as far as with PDKs. Foundries have a long history of building PDKs and build digital twins. For assembly and test, this is something that's more emerging. Things are not as standardized. And we have to be honest about that. That will be the case for you too. And so one aspect that's really important in how we help is by having very, very good relationships with our customers. So the training and the support is very, very important to be able to compensate for the things that are not standardized and not yet there. So that human aspect is a key accelerator for companies today, and you need to rely on it. You need to exploit both the digital resources and the human resources at your disposal to be able to bring products to the market. But when we speak about digital resources for PDKs, ADKs, and TDKs, so these are the digital twins of the foundry and of the assembly and testing partners. And the way we build things up, so this arrow means depends on. So the foundry PDK fits into your libraries, then fits into your design, and the TDK also fits in your design so that you can import the dependencies that exist in the digital world of your assembly partner. So in this case, this is an example of Fix, where you have one of their packages that is reflected in our ADKs, and you can import them, and you see that you have like keypad zones, loopbacks, all kinds of little details that are in fact also written down in their documentation, but the documentation is long and tedious to read. And I mean, because it's huge, like there are lots of things to take into account, and we just want to make it easier for designers to engage with the boundary conditions of the assembly process so that you can just import the ADK and layout in context and design in context so that you're less likely to make mistakes, and more importantly, you are able to get to working products faster. Look, little time check, 4 more minutes. Okay, I think we're fine. So the last step is obviously that you want to verify your design. So one thing that we do a lot is to like the regular DRC checks and fixes. So Luceda has a lot of little tricks inside that are very appreciated by designers to go and fix sharp angles, snap peering errors, and things of that sort, things that come up when you're under high pressure. We have a lot of utilities to fix these issues. And again, the support also can help to make sure you make these deadlines. But ultimately, your GDS goes into the foundry and can be manufactured. Another thing that we do in terms of verification, we have inside our platform full netlist extraction, optical and electrical. So we can extract all the electrical connectivity and the optical connectivity from your design and then simulate it or verify it against your design intent that you may have expressed in IPCIS Canvas, which is a schematic capture tool. So you can like basically verify mostly in simulation, are my connections correct? Is it what I intended to do? And some of our customers also use a 3D export feature, so you can export the entire die in assembly to the entire PIC into a 3D format so that you can put it into other CAD tools that would to be able to see it in package and things like that. So you can have the full PIC, and some people like that as well. And we also have a link with a couple of DRC checks DRC checkers. Here is an example of a new introduced one of our partner. It's called Checkmate DRC. from Spark Photonics, and we link to that just as we link with all other softwares that are adjacent to the thing we do. So now I go back to Yosef. If you're there, Yosef.
Yeah, of
All
course.
right, so we can.
Now let's start discussing the results. So we have described the idea, the tools, the procedure, and now let's go to the results. So what I'm showing on this slide that when you are introducing 7 dB losses at the Nyquist frequency, please pay your attention on the left side of the slide, the left box. The transfer function drops significantly at the Nyquist frequency. In this case, you will have a very strong inter-symbol interference. So you have to equalize the channel. On the right side, in the right box, you can see how the channel is equalized using optical equalizer. You can see very flat transfer function of this channel. Actually, the bandwidth now of the channel, it's the channel for 56 gigabaud transmission. So the bandwidth, the Nyquist frequency is around 30 gigahertz. So we can see that with optical equalizer, we can actually get very flat response function up to 40, 45 gigahertz, reducing significantly the inter-symbol interference. And now I will show, please go to the next slide, in real time how it works. Please play the video. The device, the optical signal processor, it's a programmable. You have to just push to play it.
Wait a minute. Hold on.
No, this is the next slide.
This one?
No, the previous one. The previous one also is a video. Are you in the presentation mode or not? You are not in the presentation mode. This is
no,
the
no,
reason.
I'm not.
This is the reason that you cannot play it. Now you can do it.
Yeah, okay. I know it's not, I cannot play it, Joseph. I don't know why.
Can I share my screen?
Sure, go for it.
Okay.
Well, we arranged for this. Please allow me to remind everyone attending this call that if you have any questions, please write them in the chat here. Write them in the chat, and I will make sure that they are read, and we can discuss them after the whole presentation is over in about 7 minutes. And I think there is a lot of things to talk about applications on LPO, about the equalizers. But Ben-Ezra, he's sharing the screen now, so let's assume that.
I will
Yes.
do it. Now you can see the, okay. Okay. This is, something is wrong. Okay, so I will go to to another presentation. Because something is wrong. Okay.
While Ben-Ezra goes through the next presentation, let me just quickly summarize what we have discussed so far. So we have already talked about from the perspective of NewPhotonics. We have talked already about what they see as the new applications for LPO. We also saw how the chip solutions have made a difference on the LPO systems and even reaching 200 gig per lane. He discussed also with us about the importance of the supply chain and the connectivity with Luceda, and also, of course, with the customers of Luceda and the foundry suppliers of photonic integrated circuit technology. And we will be discussing a bit on how this 200 gig per lane that he presented at OFC last year and the current developments on LPO are making a big difference. And of course, he also talked to us about the frequency equalizers and how the measurement of these scattering parameters can make a very big difference of the design and optimization of the LPO system. From the point of view of Luceda, we heard so far about the different design tools that they provide, especially focusing on the parametric design and how they can accelerate the testing solutions by working with their customers, and that's something that we can address also in the Q&A. Luceda was, of course, is an ecosystem company and they work with everyone, and that's why they are an Optica superstar. I think what we need to talk is how the lack of standardization in the testing is currently a challenge, and how this software design can actually address that challenge. Joseph Ben-Ezra, how are we doing with the sharing the video?
Okay, so I'm trying to do it, but no. Just a moment, I will try to find the right version because it was changed during the editing. So maybe we can continue with the...
Yes, I think it's a good idea.
We can continue with the existing one. Okay, Pierre, please share the presentation. I will stop my sharing, okay. Pierre, can you share the presentation? So unfortunately, I cannot show you the video, but as I mentioned, the equalizer is a programmable equalizer, and it can adjust it to any kind of channel. Please go to the next slide. Okay, to the next one, because it's also a video and I see that there's the same problem. So what you can see on this slide, you can see the performance of the channel without optical equalizer, without optical signal processor, and with a optical signal processor. You can see that on the left side, you have a very pure eye diagram. You can not measure the TDEC. When you are introducing 8 dB RF losses in the channel, and you can see the measurement of the TDEC and the improved eye diagram with optical signal processor. In this case, you can see that you can improve the performance of the system significantly. Please show the next slide. Actually, this is a summary of the performance of this optical signal processor. You can see the channel performance, the red line, without the optical signal processor using a standard electrical equalization, and you can see the bear curve. And the green one is achieved by optical signal processor. Two things are very important. You can pay your attention that when you are using the optical signal processor, you are improving the sensitivity of the channel by at least 4.5 dB. That means that you can still achieve a prefect bit error rate with about minus 9.5 dBm received power without optical equalizer. Using electrical equalization, you can just achieve the prefect bit error rate up to approximately minus 4 dBm of received optical power. It's very important when you are crossing a lot of species. The requirement is at least up to -10 dBm. So we are improving the sensitivity of the channel. And the second one, please pay your attention to the, please stay on the same. The second one, you can also see the vertical part comparison between the bit error rates, and you can see that we are improving also the bit error rate for the same received power, at least by means of a magnitude of order, in some cases even more. So this is actually the comparison between the existing solutions and between the proposed solutions and between our products. So based on a NewPhotonics solution, you are not just reducing the power, cost, complexity, latency, you are also improving the performance of the optical link. Actually, this is only existing solution for interoperability for LPO systems. And on the next slide, also, you can see the latest achievement. It was measured also for a 224 gigabit per second channel with 8 dB RF losses. You are using our optical signal processor, and you are achieving 3 dB TDEC, even for 8 dB RF loss channel, using other types of equalization, not our solution. If you are comparing, if you are not using 20 tap FFE and very sophisticated equalization techniques, if you are doing it according to the standards, you cannot achieve the acceptable performance. In this case, TDEC is not a number, so its bit error rate is really 10⁻². In our case, when we are doing channel equalization with the optical signal processor, we are achieving 10⁻⁶, 10⁻⁷ bit error rate, even for these 8 dB RF loss channels. So this is actually our achievement. Please go to the next slide. So this is a very brief summary of the key advantages. So we have a solution for solutions for 800 gigabit, 1.6 terabit data rates. We have solutions for 200 gigabit per lane. We have also the solutions for 112 gigabit per lane, but the focus and our focus is for 800 and 1.6 terabit with the 200 gigabit per second per lane. We are actually supporting multi-vendor interoperability. As I have mentioned, the device is programmable. It can self-adjust the parameters of the system for interoperability and achieving the required bit error rate. As I have mentioned and demonstrated, we are also improving the performance of the entire system by means of bit error rate, power consumption, latency, and complexity. Also a very important part. I have to mention that in our solution, the laser is integrated on the silicon photonics. We have very reliable light sources. We have very, very low losses, integrating the laser with the photonic integrated circuit, less than 0.2 dB. And what we have actually demonstrated that even if we are introducing 8 dB RF losses at the Nyquist frequency, you can still achieve the reliable communication with the 10⁻⁶, 10⁻7 bit error rate. We have also on-chip temperature monitoring in order to be able to automatically adjust our processor parameters to the environmental requirements. We are using edge coupling, and we are providing both optical and electrical design tools to our customers in order to help them easily adopt our solution and integrate them in the transceivers. Okay, thank you.
Thank you very much. Sorry, go ahead.
Okay, this is actually a summary. You can see 1.6 terabit transceiver on the top, and the pictures from last ECOC after the ceremony of best photonic component ever. Okay, thank you.
Congratulations, first of all, of course, on winning the market focus most innovative product of the year on this interconnect on the 800 gig to 1.6 tera. The floor is open for questions. I have received in the private chat a few questions which I will read for anybody in the room who has any questions for either LPO in general or for Ben-Ezra or Pierre in particular, please write them in the chat and we'll read them over the next 9 minutes. Let's start. Ben-Ezra, I think what you're doing is really fantastic. One of the people in the room is asking, can you elaborate on the key innovations that differentiate your LPO solutions with others in the industry in terms of energy efficiency and performance?
Yeah, of course, I can do it. So the key innovation is related, one of them, yeah, but the key is optical signal processor. So without the optical signal processor, for equalization, let's say you can put some equalization functionalities in drivers and in transimpedance amplifiers. But even doing it, you are actually increasing the petajoules per bit, increasing the complexity of RF design, especially at very high data rates, let's say 200 gigabit per second per lane. With photonic solution, actually, if you are going to the higher data rates, it's more simpler because higher data rates by means of photonic design, this means that it's smaller footprint. Yeah, it's it's not like RF design. So in our case, we are adding optical losses which are not significant. The optical losses we are adding with this optical signal processor are less than 1.2 dB, and power consumption of entire system, not including the drivers and TIAs, is about 5-6 watts. So if you are adding drivers and TIAs, the power consumption is less than 10 watt. Actually, the estimated power consumption is in the range of 7-8 watt, but I put 10 watt in order to be, to be sure that we are not providing you not right numbers, but we are actually carrying experiments with our products, and I think that the power consumption will less than 7 or 8 watt. So this is one of the key innovations, and innovation is also in the way the optical signal processor is working. It's actually can self adjust the network parameters in order to achieve the better performance. So this is also very important, because if you are using equalizers in drivers or in TIAs, you have some few registers, predefined registers, and they are very limited. So it's very hard to achieve the interoperability in this way. The second one, that everything is monolithically integrated on the same silicon platform, the lasers, the modulators, and also optical signal processor. It's increased reliability of the light source. It's increased dramatically the yields, because we have very reliable light source. The modulators we are using, they are also very small in footprint. We are not using silicon PN junction Mauser modulators, which are considered to be very long, about 1.5 2 millimeter. Our modulators are also very thermally stable and very compact. So the entire system integration and design also is innovative, including especially the optical signal processor.
It is very impressive what you're doing, especially those 224 gigabit per second PAM4 modulators. It's very impressive, and there are many questions from the chat which we need to go through. But let's start. And the first one is coming all the way from France, all the way from, I believe, is CA Leti. Radwan, thank you very much for being with us today. He's saying congratulations and thank you for your presentation. If I understand correctly, this represents a case of pure system innovation. Is there any potential to further improve the performance of the components within this system, such as the PN junction modulator or electro-optic modulators, to enhance overall efficiency? I think he's wondering if you can actually add new materials to have more efficient modulation.
Actually, it's not contradictory. We can use any type of materials or any type of modulators. The question is about the complexity, the cost, and manufacturability. So yeah, there are a lot of works introducing the new materials, having a better bandwidth, and having less insertion loss, improving VPP, peak to peak, etc. So once we will confident and will feel comfortable with these new devices, we can try to integrate them. We are also ourselves developing new types of modulators. So definitely, yes, if we'll have some achievements or some very advanced modulators, we can definitely consider using them. But the main idea that with optical signal processing, you can actually, even with the existing state-of-the-art modulators, you can achieve very good performance.
So we can go even faster with thin film lithium niobate or with polymer technology or with BTO. This is great news for the entire industry. We have a lot of questions for you, Ben-Ezra. I have to go really fast. The next one is anonymous. Although he identifies as Big Panda, he is asking you, how did you integrate the programmable optical equalizer? And I would like to add, is there a further room for further integration of that product?
It's very easy. It's not really integrated. It's a part of the same silicon design. So it's not really integrated. It's a part of the silicon design. You have the modulators, you have the laser on the same wafer, on the same substrate. You are implementing the optical signal processor. It can be standalone component, yeah, but it's monolithically integrated on the same silicon wafer.
The next question is for Pierre, and they are wondering about something you said during the presentation, which is TDKs, testing design kits, with the diversity and lack standardization of LPO chip designs. Testing is really a bottleneck, and they're wondering how can Luceda help?
Hello. Oh, yes. This is something new we launched, Jose. It's fairly recent, but we are looking at finding ways of putting the constraints of tests at the core of the design. And we have emerging services that are being deployed in this context of test as a service. Some foundries do it, VLC is doing it, and a couple of others. And so we are working with them to standardize how to test, what to test, when it's possible, and then accelerate design for test when we are actually it's to when everything is non-standardized when it comes to testing, and it's to bring some standardization to accelerate the time to market. So it's not everything will be standard ever, but there are some things can be the same, and so that's are the things that we are working with people that develop it as a service. So if you can go and ask somebody, yeah, please test this chip for me. What are the boundary conditions for you to do it cheaply? Well, then those are the things that we develop with those partners to accelerate that communication and yeah, by creating a digital twin for testing interfaces.
I would like to say that it is, of course, makes fantastic sense. And it is exactly the time to close the meeting. We started on time at 6 a.m. California time, where I am right now. We finish on time at 7 a.m. California time, which is 4 p.m. in beautiful Central Europe, in beautiful Belgium, where Luceda is founded. Thank you very much, everyone, for joining the call. I just put Pierre's email address in the chat. For any other questions that couldn't be answered because you couldn't finish on time, please write the answer. Many of you are here with me in California at the Optica PEC Summit. I'm going to meet many of you later today, so thank you very much for joining. And for the ones who are not here with me in California at the Optica PEC Summit, we will see each other very soon at OFC. Thank you very much for your great support. This was Jose Pozo. I had the honor of sharing a fantastic collaboration between Luceda Photonics and NewPhotonics. What can you do for them? What can they do for you? Until the next time, bye-bye.
Bye, Jose. Thank you.
Thank you. Thank you.